One miracle of modern day life is a satellite navigation system, or GPS. This system depends on 24 satellites orbiting the Earth and some relativity. This works by getting timing signals from the many different satellites, and using Einstein's theory of relativity, it calculates the distance from each satellite it has received a signal from. By triangulating this data, it can pinpoint your location within just a few yards, which is pretty impressive. Although this may be simple in concept, to do this successfully the timing signals must be accurate to just a few billionths of a second, allowing the distance calculations to be accurate to just a few yards. However, with all this motion, time and distance must be retrieved very carefully. Without the theory of relativity, the accuracy of the global positioning system would drift by more than 7 miles every day, meaning that in just a few days, your sat-nav would tell you that you're in Manchester, when really you'd actually be in Kidsgrove. What you may not realise is that relativity was not a new concept with Einstein, and that the problem of how two people address the world if one of them is moving relative to the other has been pondered for centuries. Let's start off by looking at some classical relativity that are common and we can relate to. Now the key point to remember is it's not about how fast we are moving, it's about how fast we are moving relative to something else. Let's look at an example. Imagine a truck driving at a constant 70 miles per hour. Now imagine that in the back of that truck there is a man throwing a frisbee. If he throws a frisbee at 30 miles per hour, then relative to himself, the truck, and the driver, the frisbee is moving at 30 miles per hour. Now imagine an external observer on the roadside. How fast would he see the frisbee moving? Well, he would see it moving at 100 miles per hour, as it was already moving at 70 miles per hour relative to him when the thrower was simply holding it in his hand. So this is the speed of the frisbee relative to the truck, plus the speed of the truck relative to the observer on the roadside. If the thrower turned around and threw in the other direction, then the 30 miles per hour would be subtracted from the 70 miles per hour from the perspective of the external observer. This addition and subtraction of speed relative to any measurement of velocity is the basic idea behind classical relativity. The summation of velocities has worked fine for centuries, but it is just a very, very close approximation to reality. At really high speeds, classical relativity falls apart, and this only became clear when scientists were examining the nature of the fastest thing known, which is light. When the first colour photographs were being developed, it came to be known that light was an electromagnetic wave travelling at 186,000 miles per second. However, from the point of classical relativity, the question naturally arises, relative to what? It soon became obvious that light travels at 186,000 miles per second relative to everything. But how can this be, as classical relativity tells us that there are no absolute velocities, as everything is relative to who's doing the measuring, and their motion relative to the source of the velocity? So how can both contradictory statements be right? A 26-year-old patent clerk named Albert Einstein would provide the solution to this dilemma. He accepted the idea of relative motion, but restated it as saying that any person moving in a constant velocity will observe the same laws of physics that a stationary person will observe. And as the speed of light is part of the laws of physics, then all observers will measure the same speed of light regardless of their state of motion. Now, speed is just a measure of distance covered in a given time. So to agree on the speed of light, different observers may have to disagree about distance and time. Now, how do we disagree about distance and time? Well, let's imagine we have a special clock made of two mirrors, and that the pendulum is a photon of light bouncing between them. Whenever the photon hits the bottom mirror, the clock advances 1 second. Now let's introduce a second clock. If both clocks were stationary, as the speed of light is a universal constant, then both clocks would be perfectly synchronized. Now what happens if one clock is in motion? Well, the light beam has to travel further to advance the clock, as shown in the diagram. So the time of the moving clock would run slower. This is not about clocks, it's about time itself. The speed of light is the speed limit of the universe, and therefore the only variable that can change is time itself. And this is exactly what is happening with the GPS system we mentioned earlier. This is known as time dilation, and it should be noted that a person moving with either of the clocks will notice nothing unusual, as the time difference is relative to the two clocks. Now, similar to the effect of motion has on time, there's also a relativistic effect on length as well, as remember we are disagreeing on both time and distance. Any moving object is shortened along the direction of motion. This is known as length contraction, and is the second part of Einstein's theory of relativity, resulting in a constant speed of light.